Okay, welcome everybody to our last class. Uh, let's pick it up right here. I want to focus on the cosmic microwave background for these last few slides in a little bit of detail. This is by far the greatest single piece of evidence for the whole theory that we've been talking about, the whole model of the so-called lambda cold dark model, cold dark matter model of the Big Bang. And it's from these, it's the cosmic microwave background from these three space satellites. There's been also ground telescopes that have made great contributions, but everything has been swamped now by the Planck data. Um, but just want to mention the Colby data of 1992 was a very big deal. Until then, you know, the microwave, the cosmic microwave background looked very, very homogeneous. It was just that 2.73 degrees temperature coming at us. Remember how that's done. Remember what you're looking at here. You're looking at a heat map. You take a piece of the sky, you point your telescope to a piece of the sky, and you get the spectrum. Natural light does not come in one wavelength. Okay, only lasers do that. There's always a spectrum of light. That is a number of different wavelengths, a whole band of wavelengths coming at you at different intensities, at different brightnesses. You go ahead and take all that data and map it and say, okay, if this is a black body spectrum, which is the fundamental assumption, and it is, matter of fact, this is the most perfect black body spectrum in nature. Okay, this is the closest thing to the theory of the mathematical black body that we have. That's how perfect the cosmic microwave background is. So it is. So you analyze it as a black body spectrum, and you say, okay, what temperature is creating this spectrum? And that's what's recorded. Okay, and until the Kobe satellite, the data wasn't fine enough to really see any other temperature but that overall average temperature. This was a problem because the inflation theory had been proposed in 1979, way before Kobe. And one of its most important predictions was as smooth as the cosmic microwave background is, it had to have fluctuations, as they call them, fluctuations of temperature, which mimic the fluctuations in matter density. And when that picture was shown on the left, when that data was finally produced of the fluctuations, as poor of the resolution that it is, was a very, very big deal. And the cosmologists knew that they were off and running, that they had the fundamental discovery that not only was this hot Big Bang coming from this initial plasma coming from 380,000 years after the Big Bang, but in fact the fluctuations were there as they should be. And this is why all this energy has been put into mapping the cosmic microwave background. The W map, the Wilkinson map of 2003, and now the Planck data of 2013. This Planck data is very good data. It's about as good as they really need right now in terms of its resolution to answer all the questions that they're looking at right now. I think there is something on the drawing board to actually go into even a finer dive into the cosmic microwave background, but the Planck data has been analyzed. I don't know if there's been any other physical phenomena that has been analyzed as carefully, as thoroughly, and in every different possible way. And I'm talking, of course, about mathematical analysis based upon different theories, whether it be quantum theory or general relativity theory, or the polarization of light in classical optics, or the acoustical wave forms of classical acoustics, and every other possible way. I don't know if there's been any other natural phenomena that has been analyzed as much and in greater detail and has pulled such rich information than this data, the cosmic microwave background. It is by far the single most important piece of evidence we have for the entire theory. It almost stands and falls on this thing. And that's why when we have trouble with this, when there's discrepancies coming from this analysis, there's trouble. And that's what we'll see in our last presentation. Okay, so just a perspective of what the cosmic microwave background really looks like if we had eyes to see it. It is very real, and the sky gives us kind of an idea of, oh, I see, this is what we're looking at. Wow. With the size of the sun there of a half a degree in the sky. Okay, I want to talk about three things that have been pulled from the microwave, cosmic microwave background. Two of them very important for us, given as we go forward with the last presentation. One is that the cosmic microwave background reveals to us the geometry of the universe. Okay, first of all, what does that mean? There are three possible, overall geometries that the overall universe, the observable universe, can have. It's called closed, open, flat, or should, in the order that we're looking at it, closed, flat, and open. One way to look about that is actually described by the Oxford astronomer when she talks about the crisis, that if you had two parallel lines, lines of light going, if you had a closed universe, those rays would ultimately converge somewhere in the distance. If the two parallel lines were sent out in the flat universe, they would never converge. They would be Euclidean parallel lines forever, as we know from our high school geometry. And finally, if you had two parallel lines of light sent out from a place in the open universe, it would diverge and never come back. Another way to do this is to measure a triangle in the sky, a very big triangle. Luckily, we have a very big triangle. Two sides of the triangle are two pieces of the cosmic microwave background. Take one hot spot and another hot spot. Or actually more realistically, take one side of a hot spot and the other side of a hot spot, because those can be measured. You can measure what they are supposed to be. The third side is us, our eye, our telescope. And we have a very, very large triangle in the sky. And we can measure the size of that triangle, the angles of that triangle, and see if it's less than 180 degrees, greater than 180 degrees, or equal to 180 degrees. And we can do all those measurements. So this is done in two stages. One from the theory of the lambda CMD model, and all of the theory that we've talked about, coming from that plasma that finally was loose. Finally, the radiation of this cosmic radiation was released when the atoms finally formed, when electrons finally stayed with the nuclei of the hydrogen and the helium, and this light was released. We can compute what the fluctuations should be now, what fluctuations actually there are in the cosmic microwave background. We can compute that theoretically. Then, given its incredible journey of 13.7 or 13.8 billion years through space, we can also compute what it should look like now. And we see what it looks like now, okay? And we can compare what it looks like now to what it should look like if our computations are correct. And what we find is this. We find that what the cosmic background looks like now is exactly what it should look like if we have a flat universe and it left that plasma the way we think it left. And this is the greatest piece of evidence that we have for the geometry of the universe. And we know how important this flat universe is. This tells us that the density, the matter energy density of the universe is equal to the critical density. That the density parameter, so-called, is equal to 1. It's because we have a flat geometry. The only way, in theory, that we get a flat geometry is because we have that critical density, our real density being equal to the critical density. And of course, as best we can measure the real density of the energy, taking into consideration dark matter, dark energy, and all the rest, we do in fact come up with a value which is within 0.001, I believe, of the calculated theoretical critical density. And this piece of evidence completely supports that, very, very importantly. If it didn't, we'd be in a lot of trouble. We would greatly shake our confidence in all the calculations that we've been doing. So this is a very, very important piece of information, an important conclusion that can be drawn from the cosmic microwave background. Another one which I'd like to just throw out just to show you the kinds of analysis that's being done, is that this light is also polarized. Okay, a polarized light is, remember what light is as a wave. We can think of it as a wave as a particle. Looking at it as a wave, it's a combination of an electrical and magnetic field that move through space, propagating one from another at right angles to each other. Here's a very simple picture on the left where we just focus on the electrical field, and the electrical field here is in a vertical orientation, and therefore the magnetic field, which is marked in B, is 90 degrees to it. It doesn't have to be that way. You could have an orientation, for example, in the next picture over to the right, where the electrical field is slightly bent to an orientation, was at 60 degrees from the vertical. Natural light does not come polarized. Okay, it comes like it does here in the far right. It has all different kinds of orientations. That electrical field has every single orientation, all 360 degrees. And the light is coming in this very, very jumbled way. You can filter that light using a polarizing filter. And that's what that first grid is there, the blue grid with the vertical bars. That's filtering out all of the orientations except for the vertical. Okay. You can have a very nice demonstration in high school physics class. You can take a second one of those polarizing filters and just turn it 90 degrees and have that polarized light, which is only now oscillating what's come through the filter in a vertical direction. You can go ahead and block that out with just one filter, which doesn't allow that particular orientation to get through. And so what you'll see on the other side is complete darkness. They're a very nice high school presentation that's always done. This is the basis of sunglasses, okay, polarized sunglasses, that all the light is coming through, but if the light is polarized, particularly in one kind of way, and you filter that out, you'll be dimming the light quite a bit. Okay, you won't be changing the character of the light that's coming through. It'll still be natural light, but you'll be blocking out a lot of the waves. You'll be blocking out a lot of the intensity of the light by not letting one particular orientation through, if it turns out that quite a bit of the light has that particular orientation. It's not just a random, equally random distribution of orientations throughout the whole 360. Turns out that that's what's done. Natural light is naturally polarized when you bounce it off of a horizontal, off of a surface. Also, if it refracts into a surface, it'll naturally become polarized. Obviously, we have no time. we can't go into a physics class to explain this. So take my word for it that unpolarized light on the left, when it hits a surface and bounces off, it becomes horizontally polarized. That's what your polarized sunglasses do. Your polarized sunglasses are expecting to have horizontally polarized light. That is, the electrical field is vibrating back and forth. A lot of it is vibrating back and forth in a horizontal direction, not a vertical direction. And the filter of your sunglasses is designed to not let that particular orientation through. Okay, so that's what polarized light is. Turns out that one of the great predictions of the cosmic microwave background, done, by the way, by Mr. Pebbles, of all people, our Nobel laureate of last year, the postdoc who was working with Dickey back when they got that phone call about the original discovery. He predicted that the CMB would be slightly polarized in a certain particular complex way. Why? Because if you remember about when the CMB is released, when it's finally released and decoupling, it hits those, it's released from those electrons, which have been preventing it from being released all that time. There's one final bounce, there's one final reflection of the CMB before it's released off of that surface, what they call the surface of last scattering. And this, of course, we can't go into the analysis of this. We'll have to take Pebbles' word, Jim Pebbles' word for it. But this is the pattern that can be predicted, okay? Those black lines, those little black lines, are the different orientations of the electrical fields coming from the light of the radiation of the cosmic microwave background, that black body radiation. You can see it has a very different kind of very distinct kind of pattern around the hot spots and kind of filtering through the cold spots. How they do this, guys, I have, this is mathematics way beyond me. I've never even attempted to try to follow this kind of stuff. But the point is, it was predicted way back when, and it was finally found in the degree angular scale interferometer in the South Pole in 2002. This is, again, a very, very powerful piece of evidence to support the whole model and the whole idea of what this cosmic microwave background is and where it comes from. Not only how it was composed, but how it was created. And that ultimately will bring us back right to inflation. The last one I want to look at again, if we look at this heat map one more time and remind ourselves that the heat map reflects the density map of the matter as it was released just at that moment of recombination and decoupling. When you analyze this data acoustically, what you'll find here is wave patterns, not just one wave pattern, but a very complex set of wave patterns. Think of, for example, stroking a violin string. We know that there are many, many tones and overtones in the violin. That's what gives it its character, its timbre. A different instrument will have a different set of tones and overtones. This also can be analyzed acoustically with classic acoustical analysis, Fourier analysis of sound. You engineers there will know what I'm talking about. Okay? On multiple tones and multiple overtones of frequency, and a certain analysis is predicted. Where does it come from? At a high level, remember what this is a plasma, but it's a very special kind of plasma, right? It's not just a plasma of matter. Before the photons are finally get to be released, when they're allowed to go on their way in the universe, when the electrons stop blocking them, this plasma is not only the electrons, the loose electrons, the nuclei of hydrogen and helium, but it's also the photons. The photons are trapped in this plasma. They can't get released. They can't make any progress out of it. So what you have is a tug of war between the matter, the gravity of matter pulling the dense spots in denser and denser, and then as that dense matter gives off more photons, because there's a symbol going back and forth, an equilibrium going back and forth of the photons being released from this matter, the photons being absorbed by the matter, then being released again. When the photons get released, that essentially cools the matter down, and it allows it to expand. It doesn't expand very far because then gravity will pull it back in. And there is basically a pressure wave being created around these hotspots, okay, of contraction, compression, rarefaction. Sounds like a sound wave. It is a classic sound wave. It is modeled just like an air sound wave, but in this incredibly dense, hot, strange sea of matter of this kind of plasma. This kind of wave pattern, these complex wave patterns, many, many of them are imprinted on the cosmic wave background as it's being released. Okay, one of the great predictions of this that can be studied. And you need data like the Planck data to really analyze it. That first COBE data is not going to do it at all. It doesn't have the kind of resolution to see this. I show you a picture of a field of waves to get the idea of one wavelength, but remember there are many, many different waves moving through the cosmic microwave background, these pressure undulations through and it gets frozen, it gets imprinted when it finally gets released. And so this has been predicted. It's what it should look like. And yes, it is found that the cosmic background that we are looking at has these wave imprints on them just the way they should be according to theory. A very, very powerful thing. I bring it up not because I don't think I need to convince you anymore that this is the goods in many ways, but it has an incredible consequence. This wave pattern, this complex wave pattern that's imprinted on the cosmic wave background, if the cosmic wave background heat map is also the map of the density of the plasma upon release as atoms, then this density, these wave pattern, we should see in the universe as the dark matter and the regular matter formed into the galaxies, the filaments, and the voids. We should see this very same complex statistical acoustical wave pattern in the universe at large. And we do. We do. We see it in the Sloan Digital Survey, looking back to Z's of 3 and 4 and 5. We see the same pattern, not in these quantum fluctuations, not in these atoms, not in these, heat spots, these tiny heat spots of long, long ago when the universe was small. We see it in the observable universe now, the same pattern. I hope you're impressed. This is very impressive. This is why most cosmologists do not want to leave this model. This model is incredibly powerful. Okay. Moving on, we of course looked at the simulations. We know that dark matter formed first, and actually the regular matter was just kind of along for the ride. It kind of clung around to the pockets of the filaments and voids that the dark matter created. Easy reason why, remember, the dark matter is not affected by the photons. It's not affected by radiation. This is the strange thing about dark matter. It only is affected by gravity. And so that undulation, those wave patterns were not very strong, or if at all, with dark matter. So the dark matter was able to coagulate, begin its coagulation, the densities were allowed to form and grow much sooner than the densities of the regular matter, the so-called baryonic matter, basically the primordial hydrogen and helium, tiny traces of lithium. Dark matter got a head start. Dark matter was the ones who caused the tune, and this is what we find when we simulate dark matter through these wonderful simulations, and then hook regular matter on for the ride. We get the Sloan survey. We get what we see in these fantastic surveys of the universe. Very, very powerful evidence. And the last one I'll mention is, when Gamow and his team first realized the properties of this plasma and how it would finally be released into atoms, they had the notion that all of the fundamental atoms of the periodic table would be created at that time, at the time of decoupling. Turns out that that's not the case. Be a whole course in particle physics for us to explain this. Turns out that only the hydrogen helium with these tiny traces of lithium, as we saw in that graph, can be created. There's actually not enough energy. There's not enough energy in that plasma to create anything heavier. That's not so hard to believe, right? The plasma was only 3,000 degrees. That's not a lot. That's not a lot of energy. Okay, that's not a very hot star even. Okay, so only the hydrogen and helium was be able to be created, and that's our primordial elements. Realize until the first stars began to fuse, and first of all, hydrogen is going to first of all fuse into just more helium. It's just no longer now the primordial helium. But for millions of years, right, until the first stars could start to burn their helium into carbon, and then into oxygen, and finally into iron. For 400, 500, 600 million years, the only regular matter in the universe was hydrogen and helium. There was no other elements of the periodic table. So this is a wonderful table which shows how the other processes of nature have created the rest of our elements. Okay. Any lithium and beryllium that is created in force, it has to be created in a very special way using cosmic rays. Again, no time for us to talk about that. But we finally have the small stars beginning to create the carbon, the nickel, the oxygen. The large stars will even do a better job, go further. Calcium and chromium, magnesium, some iron, copper, zinc. But you're not going to get the really heavy guys. You're not going to get the heavy lifters. You're not going to get the gold. You're not going to get uranium. You're not going to get the rest of the periodic table without much, much more energy. And that takes the supernova. The final elements of the periodic table are created in blasts of supernova. Okay, both supernova type 1s and type 2s, mostly type 2s. That's where the real energy is. And so this is just a fascinating chart to see where the ultimate elements come from. Little piece of irony, I didn't mention the steady state model. This was a rival of the Big Bang model until the cosmic microwave background killed it, a stake in its heart. But the developer, the great founder of the steady state model, astrophysicist by the name of Fred Hoyle, he's the one responsible for this analysis. He's the one who saw how the stars and the supernova could create all the rest of the elements from the nuclear chemistry. So he was made many great contributions to astrophysics. But it's interesting, he was one of the last diehards of his baby of the steady state theory. But he made a tremendous contribution to completing our current model by doing this kind of work on the nuclear analysis of the creation of the elements. Okay, as we switch venues here, Greg, do we have any questions?
Yes, we have one question from Joe Parisi, and this is regarding the geometry of the universe slide. How can an angle of a triangle be greater than 180 degrees?
Ah, that's a great question, Joe. Can I ask you to imagine a sphere? Okay, imagine the Earth. Let's go down to the equator, and let's take two lines of longitude, kind of close together, like around someplace around Brazil, the Amazon. Let's take those two lines. Let's let them go up towards the North Pole. Those two lines leave the equator. Those two longitude lines are 90 degrees to the equator. Okay, they are parallel down there. But as those two longitude lines move up the sphere, they finally meet at the North Pole. Creates a triangle. Creates a triangle on the surface of the Earth. That triangle has more than 180 degrees. You got 180 just from the two angles down below. You started with 180 degrees, 90 from each side of the two longitude lines. Whatever that angle is up at the North Pole is gravy. Okay. Now that's a two-dimensional model. Okay, to show how there can be a geometry of a space in which triangles can be greater or less than 180 degrees. Okay. The geometry of the round Earth is not flat. It is not Euclidean. Okay, so it doesn't have angles, triangles of 180 degrees. But what the CMB shows is that overall our universe does, our triangles do have angles of 180 degrees. Okay, so let us finish off our model. I call this issues and alternatives. I want to look at one issue. First of all, what are the great unanswered questions of the lambda cold dark model, cold dark matter model? Well, first of all, a little embarrassing. Cold dark matter is in the name of the model, and we don't know what dark matter is. Lambda, which is the mathematical symbol for the dark energy, that's in the name of the model, and we don't know what that is either. Okay? We don't know what created the Big Bang. We have no theory at all. The model does not just address it. Very important to realize. Okay? The model does not address where the Big Bang came from or how it started. The model actually starts with those quantum fluctuations, which somehow or other, the scalar field getting out of control explodes, and I use that word very advisedly. Expands is a much better word. Space-time expands from inflation. It does not explain where these fluctuations come from. Of course, give 3 theorists a chance and they'll give you 5 theories. And the Lawrence Krauss video of last Wednesday, is a wonderful example. He's one of the great proponents of that very nice, provocative talk. If you haven't seen that one, very provocative, very entertaining talk, him on getting something from nothing. What drove inflation? Very controversial. Okay, we'll talk about that. And finally, the question of the matter-antimatter. The idea is, at the end of inflation, with all this incredible energy being created, it turned into the matter that we know. Well, we only know how to create matter when we create antimatter. That's what we know how to do. That's what our theory tells us is being done. Not only do we not know how to, it's the only way we know how to do it, it's the only way our theory tells us it can be done. Somehow or other, this inflation field created more matter than antimatter. No one knows why. But thank God, otherwise we wouldn't be here to tell the tale. So these are just some of the great questions. These are not showstoppers. These are questions. This is what good theories are supposed to do. Theories are supposed to answer things that we know and raise new questions that we can pursue new knowledge. This is the theory doing the job of what theories do. This is the good stuff. Okay, here's the problem. Here's a problem. Here is one of the great current crises in cosmology. We go back to measuring the Hubble constant of all things, the current Hubble constant, right? We know that the Hubble constant has been changing through time because of the influence of dark matter. The rate of expansion of the universe has been changing through time. It's right now expanding at a faster rate than it was back in the past. So the Hubble constant was not always the same, but our theory can map that for us. What we do know, we have to know, is the value of the Hubble constant now. We need as accurate a number as we need now. Then our theory can tell us how the Hubble constant evolved going backwards because of the cosmic microwave background, the Sloan surveys, all the other surveys, and the quantum theory and general relativity and all of the work of the model. An important piece of data that we need is what is the value of the Hubble constant now over the last billion years, the last 2 billion years. You know, it's a great definition of now. In cosmology, 2 billion years ago is almost now. Okay, we've gotten used to that. Conceptually, one way to measure the Hubble constant is very simple. The formula is the receding velocity is equal to the Hubble constant times the distance. So go ahead, measure a whole bunch of redshifts, get the velocities from the redshifts, go ahead and get the distances, however you can, Seifert variables, type 1a supernova, get a whole bunch of redshifts and densities, do a bunch of divisions, and you'll keep getting values for the Hubble constant over and over again. Take a big average, a very fancy statistical average, and that's your value. It's conceptually not hard to describe how you would compute this number. Just do it from the data, okay? Take a lot of points where you know the velocity and you know the density, and H0 is equal to the velocity over the density. Just do the division, okay? Well, that's been done better and better using, all these incredible measurements of redshift and distance. Remember, redshift is easy, okay? Redshift, if you know what you're looking at and you can see the spectrum, none of this is engineeringly easy. My goodness, conceptually, it's very, very easy to, when you're looking at the redshift, at the spectrum, you can measure the redshift. You can see where it is as opposed to where it should be, and you can measure the redshift, okay? What's difficult, remember, is to measure the distance. That's what's hard. That's where we need those standard candles. When we're looking at something very, very far away, if we have some kind of a tell, some kind of a clue that tells us what the real brightness is out there in the vastness of space, what its real brightness is compared to the brightness that we see, we can measure the distance. That's what the period tells us for the Seifert variables. That's what the light curve tells us for the type 1a supernova coming from the explosions of the white dwarfs. When you do that, modern number right now, to measuring the Hubble constant is 73.52 plus or minus 1.62 kilometers per second per per megaparsec. Okay, those orange bands on the side are the plus and minus the 1.62. Well, that's great. We got a great number. We can use that number. Okay. Problem is, there's another way to calculate this number, and that's using, you guessed it, what a surprise, the cosmic microwave background. Yes, by analyzing the cosmic microwave background, and again, through the theory, through the model, knowing about the influence of dark energy, the changing expansions, we can calculate what the Hubble constant should be now. It's a purely theoretical calculation, not without any empirical data. There's plenty of empirical data. All the empirical data is in the cosmic microwave background, and it's incredibly sophisticated analysis. They're not doing some piece of paper computation. They're doing computations embedded in a theory, the theory of inflation, essentially, which brings everything forward from it using the data of the cosmic microwave background. That's the result that you get. You get 67.8 plus or minus 0.9 kilometers per second per megaparsec. The error bars don't even overlap. They used to. They stopped overlapping over the last 10 years or so. This is a problem. What this means is the two sets of teams, and there are many, many teams on both sides, have such confidence in their number that they don't recognize the validity of the other number. It's not even within the margin of error. They are convinced of their number, and they've got their give and take. They've got what they're willing to accept as what their errors could be in their incredible analysis of their computations and all the possible errors that go into it. You can imagine the work that's involved in coming up with this. Years of analyzing this with supercomputers, okay, using the most sophisticated mathematics, teams of people checking and rechecking and criticizing other teams, and the debates and the conferences held just on, okay, you get the idea. You have two entrenched groups here who are convinced that the other guy can't be right. Okay, maybe I'm not 73.52, but I know I'm plus or minus 1.62. If what I'm doing is correct, if what the science I'm using is correct, and that's why I'm doing it, because I think it's correct, this is the number I come up with. This is the give and take I got for you. Don't have anything else. Can't accept anything else. Otherwise, you're throwing out my work altogether. That's what each side is doing with the other side. It gets worse. Oh, it gets worse because another standard candle has been introduced into this thing, okay? By one of the great pioneers of these data measurements, a woman by the name of Wendy Friedman, very, very famous astrophysicist, now with University of Chicago. Way back then, when she was a young astronomer, she is the one who pioneered working with the Cepheid variables to get the distances out to as far as she could go. Oh, Z's of maybe a half, maybe she could get out to. But remember, we're looking for the modern Hubble constant. We want the one now, so that's fine. So she accumulated a lot of data using Cepheids, okay, and came up with a very nice number of about 72. But she's very, very well respected. She's she's an older and wiser woman now, highly respected in the community, and she has come up with another piece of these standard candles. This is the so-called cosmic distance ladder. The first one, the easiest distances, the shortest distances, is just to bounce radio beams, really, literally off of the moon, off of the atmosphere of Venus. You can get incredible measurements to within centimeters. It's ridiculous, okay? Then, of course, we have the parallax, and now with the great Gaia satellite, we can go even beyond this. This is 10 to the second. This is 100 light years. I think Gaia is now pushing 300 to 500 light years. In cosmology, it's still nothing. It's nothing. Hopefully, you can find some Cepheid variables within that radius so we can help calibration. That's where the parallax can help us. Hopefully we can even find, God forbid, a supernova within that range. Not so easy. Help that calibration. Reason why it's called a ladder is because we use the bouncing off of the radar beams to double check what the parallax shows us. We use the parallax measurements to double check the Seaford variable measurements, the things that we can measure using parallax. We use the Seaford variables that we now have confidence in because of the parallax, because of the radar, so that we can double check and calibrate the type 1a supernova. You get the idea of a ladder, one on top of the other. The next ladder of measurements is only as good as how we can calibrate it, going back to data which we feel more secure about. There are other things there in that ladder that you'll see. There's the main sequence fitting piece of this thing for the life cycle of stars. We've had no time to talk about that. And even out in great distances, there's a Tully-Fisher relationship for galaxies, which I chose not to take any time talking about. Okay, but the big prongs that we know about are the Cepheid variables and then the white dwarf supernova. The white dwarf supernova, remember, were the two teams in 1998, which showed us that the expansion of the universe is accelerating. People who won the Nobel Prize in 2011, I believe. One of those people, Martin Rees, we will come across in a moment. What Friedman and her team has found is another candle, standard candle. Remember this picture from the last presentation, I believe, with the basic life cycle of stars. On the right-hand side, you've got the heavy stars, where the cloud formation, the nebula is very, very heavy, creates a big massive star, which will then blow up into a red supergiant, finally goes supernova, type 2 supernova, and what you're left with is either a neutron star or, in really extreme cases, you've got the black hole. Okay, we weren't interested in that. We were interested in the other side, where the stars develop are of a smaller mass, because they will develop into the white dwarf, and that's where we'll get the this type 1a supernova. Well, we're still interested in this part. Friedman was interested in this part. She focused on the red giant phase of the life cycle. And once the star forms, it spends a long time in the so-called HR diagram. Everyone who's taken any of Claudio's classes knows all about the HR diagram, the Hertzsprung-Russell diagram, which describes the life cycle of stars depending upon their mass. Stars of this mass will finally go through a red giant phase. They will blow up, they'll become cooler, but they'll become much, much larger, and therefore brighter, because they're so large, even though they're not as hot. That's why they're red. Right? They're only red hot, they're not white hot. Literally the case. This will happen when the hydrogen fuel burns out, and they start burning what's left, which is the helium. The helium will burn into, carbon and oxygen, and ultimately into iron. And finally, it'll then collapse and explode. The core will collapse, the outer will explode into the planetary nebula and shrink into a white dwarf. What Friedman has identified in her team is the red giant phase has a flare phase, a phase where it flares out to its maximum brightness. That is a standard candle. By measuring the mass of the star at that form, she can predict, by calibrations of Seaford variables, what that real brightness is. It's the same story, guys, all over again, to know what the real brightness is of something very, very far away. She says that she has a way of doing this. And of course, it's all, she doesn't she say it, it's all published theory and data. She's used this new standard candle to go ahead and calculate anew the Hubble constant. Okay. And here's basically the story in a nutshell. Take a look at this with me. This is from 2000 on. This is just in the last 20 years. Look at the purple. Start off with the purple. The purple is the distance ladder, the old-fashioned way of doing it, basically with separate variables, because we're working with close. We don't really need so much, the supernova. They're for very, very far away. We're trying to get H0 now, okay, the Hubble constant now. So separate variables is really where we want to go. We can go out pretty far. with separate variables. They're quite bright. You look at the error band there. It begins with a nice number around 72, 73, but the error bands are pretty big. Look at that purple. Look at those purple circles. They stayed pretty much where they were. Okay, at the end, they end up at 74 with the shows. I'm looking now at the extreme right. You see the word shows there in white, and 74. That's the current value. Obviously, I'm rounding the numbers off. Okay, but the error bands have shrunk. Okay, from that original error band going from 80 all the way down to God knows what, 63, 64, we now have a pretty tight error band, as I showed you in the last slide. Shows is the group, the project that was done by one of the Nobel Prize winners of the 1998 data. I'll show you him in a minute. He has gone forward to map the current Hubble constant. Shows is his group. There's another one called Holy Cow, very cute name. These acronyms, they're torturous, but the letters do work in some way. They use quasars for their place of the distance ladder to go back and measure. Okay, now look at the gold or the yellow. Okay, that's the CMB measurements. Okay, that's the cosmic microwave background measurements. Okay, starting from the fundamental data of the cosmic microwave background. Look where they start. Okay, they start pretty good. That's about the same. They also start around 72, 73. There was no, and the error bands, there's no problem here. Now look at the yellow. Look as the yellow moves on. The yellow is not only shrinking down, moving away from the 72, 73, 74, but the error bands are shrinking down. Finally, where we have the Planck data, we're down here at 67 with very, very tight error bands. Okay, these people are very confident in their numbers. That confidence is based upon the lambda cold dark matter model. Given the confidence of their model, this is what gives them and the error analysis of their data. This is the confidence levels that they have. And those two measurement universes have separated. Okay, it gets worse because look at the pink. That's Wendy Friedman. Wendy Friedman started this new distance ladder, and she began starting, just working out the theory, working out the calibration. Notice that she's in around 70 with very, very wide error bands. But as she's moved along, she stayed around 70 and the error bands have gotten tighter because her data is getting more and more secure based upon her calibrations, based upon her theory of how red giants behave, given their nuclear chemistry, given what theory she's working on and relying upon. And you can see the situation right there. You can look at the last purple, the last pink, and the last yellow. Not only are the values different, but none of the error bands touch. You have three highly respected, you have a set of teams in the purple, you have a set of teams in the yellow, and you've got Wendy Friedman, who is a giant in the field, in the middle, and none of them, their professional opinion is the other two teams must be wrong because their error bands don't match. So another view of it. On the top there in green are the CMB measurements, the basic data there's from Planck and also from the Baryonic Acoustic Oscillation Probe mission. That's those waves, that's an analysis of the wave stuff. Really nice. Boy, I tell you, the model was very happy. Two completely different ways of analyzing the data, come up with a same number. You got to love that if you're a Big Bang model fan. The blue down below is a bit more mished up, but if you look at the shows there and as of March last year, and the Holy Cow people as of September of last year, 73.3, 74, not bad. Their error bands match, so they have no beef with each other in terms of someone's out in left field, and then you've got the red. the so-called tip of the red giant branch stars. And that red giant branch is talking about a branch of the HR diagram. It's in the middle, okay? And so maybe as laymen, we just want to, cut the difference. It's okay. We'll just give it to her. She's in the middle. It's where they started with anyway. But you can see it is a real problem. It is a real problem. And here's a picture from last year. Here's Adam Rees, one of the Nobel laureates of 2011, one of the two teams of the 1998 data. And you can see his slide. Is this the end? It's the Hubble constant tension problem. As you know, tension in science is a term of art. It means that we've got discrepancies here, which we think can be resolved just by better measurements. Someone maybe got a problem with their data. Maybe they're overlooking something. Maybe they got some kind of systematic data that they're not seeing. Hopefully this will be resolved. You call that a tension. You can go to a problem where now it's worse than a tension. It's like, I don't know about this. I don't know if data is going to fix this. I think there may be some, and then finally you have a crisis. And what was concluded at the end of this conference was they're in crisis, that this is something here does not compute. And you can see it right here in this 5.3 sigma, okay? How many standard deviations? Here is the cosmic microwave data up here. Here's Rees's and the distance ladder people down here. And the statistical difference between them is 5.3 sigma. And that's just in two different universes. They both can't be right. The probability is, so there's a real problem. And I thought it'd be interesting to see that this has got these people all agitated. They're having a lot of fun. They're having fun. This is very exciting. Yeah. The graduate students and the postdoc in the audience there, all they see is Nobel Prizes in front of them. That's what they see. If they can figure this out, they got themselves a Nobel Prize. This is what scientists live for. So possible solutions, well, like I say, someone's got error measurements somewhere. Someone's measuring their stuff wrong. Clean off your glass. The whole business of dark energy, is a real problem, particularly because we don't know what it is. We don't know where it comes from. It's just a term in an equation. So a lot of the model stuff is using the influence of dark energy, the changing influence of dark energy. You can easily throw a monkey wrench into some of those scenarios. And then you've got the real fundamental stuff, the crisis stuff, right? That the model, the lambda cold dark matter model is fundamentally wrong somewhere. Okay. Hello, inflation, I'm looking at you. Or looking at those distance ladder people with their general relativity and their fundamental redshift stuff. Maybe they've got some fundamentally stuff wrong with their physics. Okay, maybe gravity doesn't work So this is why they call a crisis, and they're having fun. And I do suggest that you watch the video there about that for further insight. Okay. The only thing I want to just mention briefly, just for a couple of moments here, is the multiverse. Even Alan Guth, as you can see in the video that I asked you to look at, even he now recognizes that his theory does lead to this inflation process not ending. It can continue on. Different places in an inflating universe can start its own inflation and head off in a place where that original universe would never see it in its observable universe because of the nature of the incredible exponential expansion. That Guth at first resisted this because he wanted inflation to be one thing. Well, now the problem is that what the critics put this very, very well. If inflation predicts not only our universe, but it can predict virtually any universe, because all these different inflation seeds can head off in a different direction, creating a totally different physics, a wholly different set of fundamental forces. Remember, that's where once gravity broke off, all the other fundamental forces, strong, weak, and electromagnetic, all came out of inflation. So different inflations can give you different physics. The way the critics summarize this, if you can predict everything, then you're predicting nothing. And this is where you start. So this is the idea of the multiverse. This is not parallel universes. Parallel universes is more of a quantum thing. Okay, that's a different thing, related in a way, but this is literally in our model of that scalar field creating that tremendous expansion of space-time, which then leads to the creation of matter. That process is not as simple as how Guth laid it out in his first version, and even as Steinhardt, who came across and helped him and developed it even further, that's getting this prediction out, which now everyone agrees is a valid prediction of inflation as we now understand it, is a real problem. Some people love it, some people love the multiverse, and some people hate it. Okay, and that leads us to our last two slides of Steinhardt's theory of the bounce. Okay, basically that we're back to a cyclic universe. We're back to an infinite cyclic universe. We don't have to ask the question, what happened before the Big Bang? Because there was no Big Bang. There was a contraction. We came down to not any kind of a singularity. We came down to a small, hot, dense matter, but conventional physics continued to reign. General relativity continued to hold. The standard model continued to hold. We never went to such a high temperature and a tiny volume where the energy got so enormous that our laws of physics no longer apply. That's where you are before inflation. That's where you are before inflation. Heinz says, no, let's not go there. Let's stay with the physics that we know. And so he has developed a theory where you get this contraction. That's where the smoothing out comes from. Remember, a very important property of the inflation is it smooths out the universe. So the cosmic microwave background is at fundamental 2.73 degree temperature. That kind of smoothness will come from a contraction process. And then we contract to a certain amount, and then the expansion starts again. This is his basic idea. It is not to be trifled with. He is one of the major cosmologists of the world. He is one of the original developers of the inflation theory. And if you look at the top picture here, this is basically our model in a nutshell, isn't it? We have the Big Bang, we have the rapid inflation, we have the temperature densities lead to the small densities of matter and energy, and from that we get our current structure. That's it. That's if you want to describe. And this is his model. Okay. I will leave you to watch his talk. It's a nice. He's given a number of talks out on YouTube. This is a very nice popular talk. He's talking to a popular, educated, scientifically literate audience, which is exactly who you are. And so the talk is perfect for you guys. And I encourage you to take a look at it. All right. So that's it. That's my spiel. And I did it. I've got 15 minutes for us to hang out and talk. And I'd love to hear your questions, your comments, and whatnot. So I'd like for everyone to open up their mic if they want to have something to say. Unmute yourself, you can. And Greg, could we start with anything that's in the queue?
Well, no, we can't.
Hey, I've totally overwhelmed you. So that there are no questions in the queue.
I did have a question.
Please.
Well, when I got back in, everything in the interesting. So Alan Evans had a question.
Okay.
I wrote something as a comment, but my question is, at this point in time, shouldn't SETI research be looking at the possibility of conversing with aliens already visiting the Earth?
You know, Alan, your voice is not coming through strong to me. I think it's my problem. Greg, could you repeat Alan's question to me, because your voice is much stronger?
Let me repeat.
I don't.
Can you hear me now?
I can hear you better now, Alan.
Shouldn't SETI research now be concentrating on looking at the possibility of conversing with aliens already visiting the Earth?
Aliens visiting the Earth. Alan, in all due respect, I don't want to go into that topic right now. Are there any other questions? Okay, I think what have I done? Have I hypnotized all of you? All right.
Peter, I had a question that I had in chat.
Yes.
Looking at the various somewhat conflicting theories, they seem to be using sort of as source data events going on at different distances and therefore different points in time. Are there any current theories that sort of explain this with the Hubble constant, via the Hubble constant not being a constant, and a factor that has changed over time?
Yes, all the teams are aware that the Hubble constant has been changing over time. That's not in dispute, okay? The reason why they're interested in measuring the Hubble constant now is because it's the easiest one to measure, because we don't have to go back so far in distance. We only have to go back 1 or 2 billion years in time. It's all of their models, all of their theories allow them with a very accurate value of the Hubble constant now, allows them to go ahead and calculate the varying evolutions of the Hubble constant going backwards, ultimately the age of the universe in its totality, going back to the beginning, basically of inflation. And so, yes, they are very much aware of the fact that the Hubble constant is changing, and it's in their calculations, it's in their theory. But one of the great pieces of data that they want to start with, as best they can, most accurate data they can find, is the value of the Hubble constant now, which they know is not what it was way back when.
Okay, thank you.
Peter, I put a question in the chat.
Yes.
It was about Steinhardt, and basically what I'm wondering is how complete and how destructive are these contractions that he envisions?
You'll have to listen to him. I really, I feel intimidated trying to answer. I know as much. I've done a little bit of reading about it, but I know as much listening to that talk and one or other from him. So I feel intimidated in really answering that question.
Is there anyone else? Is there anyone else who proposes that theory? Because
yes, no, he's getting some. First of all, he has a team of people, particularly on the simulation side. So they've now begun to simulate these bounces using the same kind of simulation technology, the supercomputers, just as the the evolution of the galaxies and superclusters. They're now simulating these bounces of contractions and expansions, and they say they're having great progress. So no, he's not, by no means is he alone. Can I interrupt before we continue, and maybe just give you guys a bit more idea of questions while I'm talking. I'd like to talk about what I'm going to be teaching in the spring, starting in March. I thought what might be interesting is to have a course in quantum physics. Since we've touched upon it here in our cosmology course, we really didn't get much of a chance to explore it, but we certainly have seen that it is very, very central to cosmology and to so much, of course, to everything. It is the bedrock theory of all of physics. Certainly, general relativity also plays a very, very fundamental role in our subject, but quantum theory really is the bedrock of it all. And I thought it might interest people to do a course in that. 3 or 4 years ago, I gave a year course that combined quantum theory and radioactivity, and we got up as far as the creation of the atom bomb. We got up as far as as the war. What I'm thinking here will be a one-term course, just a course in the spring, and it wouldn't be so historical. It would be more trying to do, contemporary stuff. It's very important to do a little bit of the history of quantum theory because it really does set the stage. It shows you where it comes from. It's kind of like understanding where inflation comes from in our theory. You have to kind of understand the flatness problem, and the horizon problem of why the inflation theory was even proposed. To understand the modern theory of quantum mechanics, you have to really know where it came from in the Bohr theory to see how these new ideas developed. But the emphasis will not be on just the history of it, but really trying to go further, particularly what we have just 8 classes, and the radioactivity that we need, which is a fascinating story. I very much enjoyed doing that. I think the class back then enjoyed doing the parallel story of both radioactivity and quantum theory. We'll just summarize the radioactivity story as we need it and not going through so much of the history. So that was my thought of offering that in the spring, in March, and I thought I hope it'll interest some of you. Okay, any other thoughts about what I just said about that, or anything else about our class?
Peter?
I look forward to coming to your new course.
I'm sorry?
Peter.
I look forward to coming to your new course.
Great, Alan. I look forward to your questions. You ask a mean set of questions, my friend. Someone else.
Peter? Go ahead.
Yes. Go ahead.
Go ahead, Mary.
Okay, quickly. It's related to that video, So Much Universe, So Little Time. And this is maybe, because I don't know physics or anything, but the statement was made, I've forgotten who the man was. The universe is older than itself.
Yeah, that's a terrible thing. That's
Kind of glib.
Yeah, it's glib. It's supposed to be sexy. It's supposed to catch people's attention. If you're not interested, then you're not interested. To say provocative, silly things like that to try to get your interest, I'm really against that kind of stuff. Okay, what it means is that there are 2 different ages. Okay, one different than the other. So one is older than the other. Okay. What they're trying to imply is that one age is better than the other, so this age is older than itself. It's I don't know. It's silly. It's all right. Don't get me started. Anything else?
I have a real low-life question. As an English teacher, I have no background for this class. I'm trying to wrap my mind around the flat universe. If I look up in the sky and I see things going in all different directions, I would picture the universe as being more spherical. Is it flat like a pancake? I don't.
No, it's I guess in a sense it's a terrible word. Okay, it's not flat like that at all. It's flat like Euclidean geometry of high school. It follows those postulates. That's why we call it flat. It's a terrible word. It's just like dark energy and dark matter. They're terrible words. First of all, it sounds like dark energy and dark matter must be related. They're both dark, aren't they? No, they have nothing to do with each other. Okay, the words are terrible, but flat is a word that is deep in the lexicon, and it comes from the flat geometry of Euclid compared to the non-Euclidean geometry of Riemann, of curved geometry, curved and flat, and that's where these words come from. So yes, the observable universe is spherical by definition. We can look in any direction we like as far as our telescopes will see, basically to the cosmic microwave background. We can't see any further back than that. So the universe is spherical in that sense. But the way, for example, light waves behave, the way parallel light waves behave as they move out through space, do they move according to a flat geometry or a curved geometry? We can measure that, we can answer that question by looking at the cosmic microwave background, seeing how it looks like to us now, what
We're losing you.
is in the sky compared
You're
to what
gone, Peter.
I'm sorry.
We lost you.
Oh, you
Your
lost me.
voice, yeah,
Okay,
like
yeah.
the last 30 seconds of your voice went away.
Okay, yeah,
I can
I just
still
got
hear
that
you.
I just got that unstable message. I'm sorry. We're struggling here for the end. So the point is that the flat geometry, the Euclidean
No,
geometry,
you're breaking up.
breaking up. All right, let me hold on a second here. Am I coming back? Hello? Hello? I'm totally gone, huh?
Hello? Yep.
Yes, we can hear you.
Okay. The flat geometry, the Euclidean geometry can
No,
be
you're
measured-
here. Or no?
No? All right, guys. Why don't we
No.
stop this frustration? I apologize. I think it's me. I think it's on my side. It could be this damp weather and stuff.
Yep.
You're
Right.
much better.
Much better. Well, in the much better vein, let me say goodbye. Let me say how much I enjoyed this class. You guys were great. Questions were great. And I appreciate your attention.
But Peter, quickly, please, what term would you substitute for flat?
Euclidean,
Well, no,
Much-
I mean,
much better word.
I
much
mean,
better
in the layman's term. In
Geometry of
layman's
the
term.
universe follows the 5 postulates of Euclid,
Okay.
not the postulates of Riemann and Lobachevsky.
Thank
So-
you very much. It's been most stimulating. Peter.
Fantastic.
Thank you for opening my eyes to a wide world.
Okay, guys. I hope to see you in the spring.
Thank you.
Thank you, Peter.
Okay. Bye-bye.
Thanks, Peter.